Hey, Mr. Dimitrowicz, it's great to be back with you.
It's great to see you again here. Let's learn some stuff. Yeah.
Yeah, some really cool stuff today. We're going to start learning about like atoms, and atoms are like crazy cool. And I know you're going to help us understand like the history of the atom. So why don't you take it away?
Yeah. So one of the things that I want you to keep in mind here when we're doing all of this is that these guys, these brilliant scientists, they were trying to figure out what the atom looks like, and what you're taught in grade school, that is way more than they knew. So have a little mercy.
So, Mr. Dimitrowicz, John Dalton was the first guy. He's the first dead white guy that we're going to look at. Tell me about his view of the atom.
So he essentially said, well, the fact that he thought there were atoms is kind of a big deal because the Greeks said there were atoms 2,000 years ago, and then nobody touched them because nobody could see them. And then Dalton came along and said, yeah, there are atoms. And he thought they looked like these billiard balls that we have drawn here on the screen.
And you know, he was kind of right, because they do look like billiard balls, but let's kind of talk about the things that he learned about the atom. I think that this is like 1600s, maybe 1700s. He's doing this work.
Yeah. Again, he came up with some statements, and when you see these statements, you're going to be like, oh, come on, man. But you need to understand that no one knew anything about the atom. And if you picture in your mind like this amphitheater full of people, and everything that he said, all these statements that Mr. Bergman is going to write down right now, they were mind shattering. So picture like uproarious applause for each one of these. But let's go through these points one by one. Mr. Bergman, will you write out the first point for us, please?
So it says here that matter is composed of small particles called atoms. So why that sort of seems obvious to me, right? But
yeah, again, we as in our elementary school, we know this, but you need to realize that people didn't think that they knew anything about what was around them. So him saying that everything around us is made up of atoms is kind of a big deal.
yeah. Number two, he said this. Atoms of the same element are identical, and different atoms have different properties. Now,
Again,
that's
yeah.
mind-boggling that he said this. It seems so, like we sort of know this, but why was this earth-shattering in his day?
Well, I mean, if you take a look at how he thought the atom looked, he thought it looked like a big ball, right? And so were other atoms of different things different? Did they look different? So him coming up with the idea like, and again, for us, we're gonna be like, really? But like a copper atom, it's gonna be the same as other copper atoms, or gold atoms are the same as other gold atoms. Him saying that out loud let people know that atoms actually were different for different things. So that's kind of a
And
big deal.
so it's as if like you've got big spheres and small spheres. So like a gold atom would be a big sphere, and a little hydrogen atom would be a little sphere, but they're still all spherical, if you will. All right, the third one is this. Atoms can't be created or destroyed.
Now that one probably caused some controversy because people of the day were probably like, whoa, 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 wait, I can light things on fire and it destroys them. But the idea that everything's made up of atoms and the individual particles couldn't be destroyed was kind of a big deal. In fact, there's a law of the universe, and there's very few of them, that says matter cannot be created nor destroyed. It can change forms, and since matter is made up of atoms, yeah, big deal.
That's weird. Like when you burn something, it seems like it's destroyed, but actually the atoms just move around.
They
Number
do. We'll talk
four
about that.
is this. Atoms combine in whole number ratios.
This is kind of a big deal as well, right? Because people didn't even know atoms existed. And now he's saying, oh, by the way, we can put them together. But I think the key part of this is that they're in whole number ratios. You can't have part of an atom, right, Mr. Bergman?
No, you can only have either a whole atom or another whole atom. You could, yeah. All right, and then the last one is this. In chemical reactions, atoms combine, separate, and rearrange.
So I guess the question comes up, like, how do atoms interact? And they didn't know, like, yeah, sure, atoms exist. Bravo, Mr. Dalton, but what do they actually do? And so he said, oh, by the way, they can connect with each other and they can actually form new things. And that's essentially what the last point of this says. Correct, Mr. Bergman?
Yeah, that's exactly right. So, Mr. Dimitrowicz, now I think we've got an interesting thing is that Dalton basically saw the atom as spheres, and then a more advanced version came from this dude, J.J. Thomson. Tell me about it.
Well, I love the fact that you called this guy that looks like this a dude. That's super awesome. The atom, essentially, it evolves over time, the views of it. And J.J. Thomson's like, hey, maybe it is a solid sphere, maybe it isn't. And he came up with this really ingenious experiment. So essentially what he did is he took a piece of metal right here, and he put it in this cathode ray tube. And then what he did is he noticed that something shot out from that tube. And he discovered that when he changed the charge on the outside of the tube, it caused that beam to shift. So if you take a look right here, see how there's a negative plate down below here? And you see that this negative plate is causing the beam to push up. Well, that's a big deal.
In fact, let's take a look at what that might actually really look like. Let's watch this guy do it.
Let's do it.
Now that was super cool. I could see how that light got moved by that magnet. That's really super awesome. So, but what did that tell us about the atom?
Well, so that must mean that this beam that was shot out, and you saw it in the video, if it gets bent by a negative charge, it must mean that this beam is negatively charged. Well, where did that beam come from? It came from the metal that has a bunch of atoms in it. Well, what does that mean to us? Well, therefore, if the metal's made up of atoms, and the atom have negatives in them, that means that our atoms can't be these solid balls. Also, Mr. Bergman, aren't atoms neutral?
So I think it's telling us two things, right? Because if an atom is normally neutral, has no charge, and something negative shoots out, that means there's got to be positive parts to the atom. So it gives us the fact that the atom is made up of both negative and positive.
Right.
So he's still like the sphere thing. So he still says atoms are this spherical thing, but they're made up of some kind of particles that have charge.
Yeah, and so the new view, and again, you need to understand where he's coming from. He came up with the idea, and you can see this here on the board. He came up with the idea of the plum pudding model, which, by the way, this is what plum pudding actually looks like. I think, Mr. Bergman, you have a better way of viewing it, a better thing.
If I have an addiction, it's to chocolate chip cookies, and think of chocolate chip cookie dough, and the chips represent the electrons, the negatively charged particles, and then the dough is positive. So you probably remember that there's things called protons. You understand it from your atom, but the reality is Thomson didn't know that. So he thought the dough was positive, if you will, and the chips were negative.
So in essence, the positive and negatives were just interspersed all the way around. And what's kind of cool about this is that while it's a big improvement over the solid billiard ball model, it's not quite right, is it, Mr. Bergman?
Right, and that leads us to another dead white guy, Ernest Rutherford. He was like some Sir guy from England, right? And so tell us, he did a really weird experiment. Tell us about that experiment.
Yeah, this is actually uber cool, trying to relate to you with the language here. What he did is he took a really, really, really thin piece of gold foil. And so the gold foil was about 10,000 atoms thick. And you may think to yourself, 10,000 atoms, that's huge. But in reality, it isn't. 10,000 atoms is would look at a piece of your hair and be like, ooh, that's big. So get a picture of a very, very finely thin piece of gold foil. And then he shot these alpha particles, which are essentially these big fat positives, at the gold foil. Now, what did he expect was going to happen here, Mr. Bergman?
Well, he kind of expected them to like bounce and stuff like that, right? To go through it, actually, because it was so thin.
So try that one again here.
Yeah, I said it wrong.
To go straight there. Yeah.
So because it was so thin, because he thought it was so thin, he thought it was just going to shoot right through it.
Yeah, and so he at the first he sees this gold foil, and how he couldn't see atoms. So what he did is he put this fluorescent screen around it that would light up wherever it hit. And so over and over again, this positive particle hitting the wall, hitting the wall, hitting the wall, and then one out of every 3,000 times, or approximately, actually I think it's one every 6,000, but I have to verify that. You'd have this random hit to the side, like this right here, and he's like, that can't possibly be the case.
In fact, I think he said something crazy like this: as if I shot a cannonball at a piece of tissue paper and it came back and it hit me.
That's crazy, right? So he said that the idea of the atom being these positives and negatives randomly interspersed, this is my impression of this positive negative interspersed, couldn't be the case because this big fat positive would just roll right through. But he said if instead all the positives were really, really compact and in the center, if that alpha particle flew through here and hit that, it could actually ricochet off.
So this is the discovery of the nucleus, guys. What he discovered a very small, dense, positively charged thing that we now know is the nucleus of the atom, and the electrons are interspersed on the outside. So Thomson was wrong. He had the idea, the positives and negatives, but he didn't realize that the positives were all concentrated on this little itty bitty spot in the middle of the atom.
So when you take a look at our interpretation of the atom now, see this big fat positive in the center? So the alpha particles come through here. Now, the majority of the time, they don't, and they go straight through and they don't hit. And we're going to watch in our next video, we're going to see how small the atom actually is, and it'll make a little more sense. But Mr. Bergman, this is actually very close to the view of the atom we have now, a positive center and negatives on the outside.
Absolutely.
But there's one piece of the subatomic particle trilogy, protons, electrons, and there's one more thing that they've not accounted for.
And you probably remember this from middle school science, guys. It was called neutrons, right? And so it took this next dead white guy, Chadwick, to figure that out. And tell me about how did he figure out the whole neutron piece?
Well, again, this falls in the category of beyond the scope of what we need to know, which I know is not great. But in essence, he was able to figure out the masses of the actual atoms. And again, beyond the scope of what we need to know. And every time with just protons and electrons, it didn't match up with the masses that he was getting. So there had to be something else. And he knew it couldn't be more positive or negatives because that would make an atom charged. So he came up with this essentially dead weight, ballast, if you would, these neutrons. And all these neutrons essentially do is they make things heavier. And why does that matter? Well, heavier things move differently. Mr. Bergman and myself, I would wager to say right now that I move a little bit differently than you do. Is that fair?
Probably so.
Fat shaming on myself, and that's okay to do. But it is a big deal that we understand how neutrons work and how they're in the nucleus, because that's going to allow us to set up when we start talking about the rest of the atom.
Right. And the next part is, there's one more guy we got to talk about here, and then we'll close, is this guy named Niels Bohr. So what Niels did is, so we've got the central dense nucleus and the electrons kind of on the outside, but he was able to define where on the outside the electrons were. And so much of chemistry is really about the electrons on the outside. So we got to talk about Bohr. So what's Bohr's addition to this whole saga of the history of the atom?
So you need to understand that, again, we're progressing along the way. And so Rutherford said, hey, there's a positive nucleus and electrons somewhere on the outside, right? Which begs the question, by the way, and we're going to answer that a little bit, is why weren't the negative charges, remember, opposite attract, getting sucked into the nucleus? We'll talk about that a bit later. But Bohr said, you know what? These electrons are actually in these energy levels surrounding the nucleus. Now, he came up with the idea of these energy levels or shells, essentially circles. And they would go in those circles, and if the electrons gained or lost energy, they could move up or they could move down in these energy levels.
And we'll get into a lot of detail about that later on in the course and what that does. But what proved, how was he able to figure that out, that the electron levels exist in these shells?
So what essentially he was able to do is this, and you guys will talk about this a lot more, but when electrons jump up in an atom and then they fall back down, they give off energy. And that energy can come in the form of light. And so if you're looking at an atom and you excite the electrons, give it energy, and the electrons jump up and fall back down, you're going to see lines, and every single line represents an energy fall down. Now, how did that look exactly? Well, we're going to play around with this in a bit, but do you see how here, these are these spectrum. You see how there are these 4 different lines here for hydrogen? These 4 different lines, they represent energy fall downs that electrons make from a higher energy level to a lower energy level. So if you see for hydrogen and helium, there's a certain number of energy levels. And he came up with the idea, Mr. Bergman, that aren't there 7 energy levels in the atom?
Yeah, so there's like 7 energy levels, and there's a certain number of electrons in each of them, and we're going to talk about that later. So guys, if we're going to summarize, the first model of the atom was a sphere, or like different size spheres. That's Dalton. And then Thomson, right, he's got the spherical chocolate chip cookie model. And then Rutherford says he's got the central dense nucleus and the electrons on the outside. And then Bohr, he's still got the central dense nucleus, and he now has the electrons existing in these shells on the outside. And that's kind of where we're at. There's a little bit more to it. I think that's a good progression of what we've been learning in this video.